Still looking at trig, but this time trig substitutions. I mentioned it before, but when you've got the square root and you see sum of two squares, difference of two squares, then a trig substitution can be handy. So sum of two squares, we do x equals a tan theta. If I've got difference of two squares where it's a squared minus x squared, then either sine or cos, whichever one. And if it's the other way around, x squared minus a squared, we can use a sec. 1 on the square root of a squared plus x squared. You remember this was one of the non-standard integrals. Well, let's see where it comes from. So I would do the substitution a tan theta. So dx is a sec squared theta to theta. Subbing it in, this is what we get. Now, 1 plus tan squared is sec squared. So we've got a squared sec squared. Square root of that is a sec. Cancels with the a sec squared on top. And we just have the integral of sec. And we know the integral of sec is the log of sec plus tan. So how do we get theta back in? Let's draw ourselves up a triangle, because we just said x is a tan theta, so tan theta is x on a. Hypotenuse, no coincidence, it is our square root. We just read off, and you might think, well, hang on, that's not what I said the log was. That's because of the divided by a. But I could use my log laws, and really that's just another constant. And so we do get that non-standard integral that we saw before. So that's where it comes from. Let's do this one. X on the square root of 1 minus x squared, and for some insane reason we don't notice we have a derivative on top there, because derivative of x squared of course is minus 2x. We don't spot it, and we go, ah yes, square root, so I'll do the substitution x equals sine theta for this one. So dx is cos theta to theta. Subbing in, 1 minus sine squared is cos squared. Square root of cos squared is cos. Integral of sine, integrate sine, we get minus cos. Draw myself a triangle, in this case opposite over hypotenuse, adjacent, again no coincidence, there it is, square root of 1 minus x squared. Substitute back in, and we get the answer that we were hopefully expecting if we'd done it the other way. Square root of x squared plus 3, so I'll do root 3 tan theta, dx is root 3 sec squared. Sub in, you notice I didn't actually bother writing the square root of what would have been 3 tan squared. I went straight to root 3 sec on that to save myself some time. What do we get? Oh yes, root 3 times root 3. Oh no, sec cubed. This is when we just start crying. Got to do it by parts. Let's split it. Sec theta into sec squared. U will be sec, du is sec tan, to v is sec squared, v is tan. So we get 3 lots of uv minus 3 lots of the integral of sec theta tan squared theta. Okay, split that up into two things. Integral of sec we can do, log of sec plus tan. Draw up a triangle, let's substitute back in. And this is what we get. 3 times the square root of x squared plus 3 on root 3 times x on root 3 minus the integral of, this is where we're going to have to be careful, because look, it did say 3 sec cubed. Very tempting to leave the 3 there, but if you read back through your solution, that's 3 sec cubed becomes this, because read the first line and the third line. The square root of x squared plus 3 is 3 sec cubed. So when I sub back in here for the 3 sec cubed, it's just one lot of solve the integral, the square root of x squared plus 3. Very easy to make a mistake and make that minus 3 lots, and then obviously you're out by a factor there. But let's move that over now. So we have 2 lots of the square root of x squared plus 3. Divide everything by 2. And I think we have it. That looks like an answer. Oh, I know what I probably did. Both of these are over the square root of 3. So I probably pulled that out and put it into the constant. Just looks a bit neater. You don't have to. I mean, that's certainly an answer to the line before. It just means that the constant would be different if you were working out a constant. There's our answer. Now, this comes out of the old Patel textbook. There's not an exercise on it in the Cambridge. Not sure why not. It's a handy thing to use. But we'll have a go at some of these.